All right, let's go and get started. A couple things. So number one, your homework 5, if you haven't already turned that in, it's due today. I've got a pile set up over there. Let's see, a couple other things. So let's see. So we have our exam coming up on April 5th, which I'm going to, again, start at 9:55 a.m. I did this in steel design. I think it's especially prudent to do this in concrete design because I, again, have a lot of handouts left up here, which if, I print off one for every student. So if I've got a lot of handouts, that means somebody's missing them. So here's what I'm going to do. I have the notebook set up, good to go. All right, so I'm going to go ahead and start to pass this out. I've got the sign-in sheet here. What's up? No, there were handouts like last time and the time before. So, but I've still got quite a few. So, which by the way, I have one for you as well. If you're missing a handout, tell me on the sign-in sheet, and I will bring them. But if you're missing some of the newer handouts, chances are they're up here, and come see me after class, and I can give them to you now. But indicate it anyways. So here's that. Okay. So the sign-in sheet is in the binder, and with that, I think we can probably go ahead and kind of get started on concrete today. Not to say that we're going to go fast, but but just a heads up, guys, we are actually a little behind on the schedule, so I do want to try and make up some steam, or pick up some steam and get through some stuff. So if you've got any questions, please, don't hesitate, but I do want to try and move forward some of this stuff pretty expeditiously. All right. All right. Let's have okay, all right. So last time, if you recall, we were discussing shear. We ended our discussion of doubly reinforced sections, and we got into the world of shear. Now, I showed you some videos, and we talked a little bit about the behavior of concrete and shear and how, it cracks at 45-degree angles, and when it fails and when it cracks, it goes quick, so its phi value tends to be a little lower, and what have you. But I do want to get into some examples, and not only on analysis, but on design. Before we begin, a couple things. I will say that the structural analysis demands for shear are probably the heaviest that they are in any of the other topics, so you really need to make sure you understand shear diagrams and the equations for shear diagrams and all of that, because that is going to be incredibly important as we start to not only assess whether or not a beam meets shear demand, but also how to design for shear, because that stuff's pretty important. So, all right, so I want to start here. This is the shear resistance provided by the concrete. Maybe I should start one slide back. Ultimately, our design capacity must be greater than or equal to our design loads. So phi Vn has to be greater than or equal to Vu. So our nominal capacity for shear is pretty simple. It's just sum of forces. So the sum are the shear strength provided by the concrete and the shear strength provided by the steel. And no matter what, for shear, phi is 0.75. So there's no calculation or assuming a phi or anything like that. Phi is just 0.75. So pretty simple. What's that? That's a good question. And the answer primarily relates to ductility. If you recall from bending, the level of safety associated with a beam was related to how much strain you could develop in the steel. Make sense? And based on different beam proportions, you can get different levels of strain in the steel. Well, what I'm saying is that under shear, there are changes, but they aren't appreciable enough. In other words, the beam can be proportioned anyway, and in the end, its shear behavior doesn't really change. It's just going to fail, and when it fails quick. So that's why we can just sort of cap off the phi at 0.75. That's a good question. Did I answer that? Everybody else okay with that? Okay. So let's go into the shear strength provided by the concrete. So it's 2 lambda BD square root of FC prime. So B or B sub W is the width of the beam, or if you have a T beam, it's the width of the web. D is the effective depth, from the top of the beam to the tensile steel, and square root of FC prime. Remember, square root of FC prime, put in PSI, get out PSI. So don't forget that. And then our lightweight aggregate factors. That's pretty straightforward. Okay. The shear resistance provided by the steel is just the area times the yield stress times D over S. We'll talk about the area here in a second, but the D over S is essentially the number of stirrups per beam depth. And the reason why is if we assume a 45-degree crack, that D over S, we're just trying to determine about how many stirrups can we assume will be present over a crack in shear. So this diagram would kind of illustrate that there'd be about 4 stirrups throughout a given crack. So for this example, the capacity would be the area of one stirrup times the yield stress of a stirrup times, in this case, 4, because it's 4 stirrups across that given crack. Sound good? All right. Now the area, be real careful on that. The area, or that A sub B, is essentially the area of the steel across a given crack. So a very common stirrup shape is a U-shape or a hoop-shaped stirrup. So in this instance, if I'm cutting across that crack and I'm looking at a given stirrup, the area of that stirrup is not the area of a single number 3, it's the area of 2 number 3s, because there's 2 number 3s per stirrup. Does that make sense? So if it's a number 3 stirrup, the A sub V is not going to be 0.11 square inches, it's going to be 0.2 square inches. So you might have an instance that's like this or this, where it would be 2 times the area of a bar. This would be 1 times the area of a bar. And then if you've got a heavy column section, you got 4 times the area of a bar. So yeah. Sound good? Any questions? I guess I don't need them. I screen captured this from another set of notes, and I didn't want to go through and edit all the points out, so I just kept them both there. I'd have to go through and do the Photoshop to increase the clarity. I didn't want to do that. I'm lazy. You all should know by now I tend to go with the lazy route when I can, right?
So ever ask why you're doing something
Not always, but it's not an unreasonable assumption. Not an unreasonable assumption. All right. So, yeah, no real reason. But any other questions? Okay, a couple notes in regards to stirrups. We have a couple limits in regards to reinforcement, not just from an area standpoint, but also from a spacing standpoint. For instance, the minimum area of a stirrup is pretty easy to compute, and we are going to use that later on from a design standpoint. We're not really going to worry about this from an analysis standpoint, but it's going to help us out later on when we try and design. So essentially, these limits are just trying to ensure that there's enough steel there to prevent a sudden failure. I mean, you all saw what happened when you had a shear failure and it went quick. Well, sort of the situation with these limits, we're just trying to ensure that we have at least enough steel. So we have a minimum area requirement based on a given spacing, and we also have a maximum spacing that we're allowed. So no matter what, in most regions of the beam, we have to provide at least some level of stirrups. Even if we don't need them, we just need them there from a safety standpoint. Everybody okay with this so far? Okay. Now, I've given you the answer for this example, and it looks like this. But I want to get there. I want to see how we're going to get there. So what we've got here is a beam that's 4 KSI concrete, 60 KSI steel. Now, if you notice, I'm saying F sub YT is 60 KSI. I don't really care about this steel for this example. I don't care about these 3 bars. I care about the stirrups. Okay. Now, I've got normal weight concrete, so all that tells us is my lambda value is 1. It's a simply supported beam that's 24 feet long, and it's got number 3 stirrups utilized. Now the loads are 1.3 kips per foot and 3 kips per foot in dead and live. I guess the big point to discuss would be this. Okay, ooh, about spilled that. Okay, now if you notice, I've got different stirrup regions, but notice how the stirrups are spaced differently as you go out from the span. Yes?
You don't take into consideration the reinforcing steel at the bottom, but what the failure paths still go through those.
Sure, yeah, but what I'm saying is those bars are not resisting the shear forces. They're resisting the moments. The vertical bars are the ones that are resisting the shear.
The bottom ones, will they resist a little bit of shear maybe, or no?
Not appreciably enough, not enough to arrest those cracks. Now, you can, there are provisions for taking a stirrup and actually inclining it this way along the crack to resist it better, but these just aren't really going to do any good. I mean, by the time you've cracked through all of this, the beam's done. So, I mean, yeah, I see what you're saying, but from a safety standpoint, if you've got a full depth 45-degree crack going right through that, we're good. Beam's done. I'm not standing on the beam. That's just me. I'm good.
Is the reason why they're
What?
He said, what about grandma? You put grandma out there.
is the reason why the regions are divided up that way because you're getting more shear at the support?
Exactly right. Here's our shear diagram, right? I mean, what does the shear diagram look like for a beam that's simply supported with the uniformly distributed load? You got high shears up here, low shears in the middle. So we put more stirrups on the end than we do in the middle. Exactly right. One other point I want to mention, and I'll get to this. I'm not using 3.65827 inch spacing. It's simple. 4-inch spacing, 8-inch spacing, 10-inch spacing. Keep it simple. All right? Yes? That's a good question. And we have got 2 design examples. One that looks like this and one that looks like that. We will handle it.
Space them incrementally like that, just for simplicity.
Yeah, yes.
It makes more sense to like gradually do it instead of these are 4 inches and these are 8.
That's a good question. And yes, we do try and do discrete sort of lumps of stirrup spacing. So we might have so many at 4 inches and then so many at 8 inches and then so many at 12 inches. Now, let me say this. You should do your best to generate an economical design, but not one that's incredibly complicated. And there is a balancing act there, and I'll be the first person to admit it. What I'll say is this. I think it ultimately depends on your application. In other words, if this one beam is going to be repeated 800 times in a given structure, it might behoove me to generate a stirrup spacing that's a little more refined. Because if I space my stirrups out a little bit better and I'm able to eliminate a few stirrups, well, that might not really matter for this one beam, but a few stirrups off this one beam times 800, that's a lot of steel that I'm saving, a lot of time that I'm saving, and ultimately a lot of money that I'm saving. Does that make sense? Let me also say this. We'll be better equipped to discuss stirrup layouts when we actually are doing stirrup layouts. Like here I'm giving you one and I'm just saying let's do the capacity. But later on, I mean, I'm going to give you an example where I'm saying, you know, here's the beam, lay out the stirrups. You see what I mean? So it'll be a little easier to have that discussion later on. That make sense? We will get to that though, I promise. All right, everybody good? Now now I've got this WD is 1.5 kips per foot. One of the things that you weren't given is the self-weight, but we're going to have to go through and compute that because it's going to have to support its own self-weight as well. Okay. Let's get into some calcs with this.
How come we take in the self-weight
Okay, I've gone into this before, but if you remember, the self-weight of concrete by itself is about 145 pounds per cubic foot. We don't use 145, we use 150. So we're bumping that up a little bit to account for the extra steel, yes.
Similar question. So like the 150, we're just assuming that's the same for singly reinforced, doubly reinforced,
Yeah.
stirrup, without stirrups.
Yeah, again, if you want, we can be a little more detailed in it. It's just going to take longer, and it's not going to appreciably change your answer. I mean, I'm telling you. I mean, we can go through and do it if you want. I'm telling you, 150 is going to account for it. Look, if you design a beam and you use 6 number 9s as opposed to 7 number 9s, okay? Yeah, the 7 number 9, yeah, the beam's going to be a little heavier. A little heavier. You'll never know it. I mean, it's not going to affect your design loads at all, really. I mean, yeah, your beam's going to be slightly heavier, but we're talking a few pounds on the order of kips. It doesn't matter. You okay with, I mean, we can go through it if you want.
I was just asking if we did remember.
No, we don't. All right. So let's get into this example. A few things we need right off the bat are some material values. All right. So what can you tell me about the concrete? We know it's 4 KSI, but what else can you tell me about the concrete? Normal weight. So for the concrete, we know that FC prime is 4 KSI, but what else do we know? We know lambda equals 1, and we know that gamma is going to be 0.15 kips per cubic foot. And for the steel, FYT is 60 KSI. Okay. Everybody, and beta 1's 0.85. Although we actually don't need it for this example. I mean, I'll go ahead and write it out, but we won't use it. And the reason why is beta 1, if you recall, beta 1 will tell you the relationship between A and C for your stress block in bending. And since we're not doing any bending, it won't really matter. So, but it's good that you recognize that. Okay. Now the beam geometry. All right. Now, we've got a beam that's how long? All right, 24 feet. I'm going to go ahead and convert that and say it's 288 inches. We have a B value of 12 inches. What was D? And what's H? Okay. Now, what are the size of the stirrups? Number 3s. Okay, so if we have number 3 stirrups, all right, we know that the area of a number 3 is 0.11 square inches, but what that means is that the area in shear is 0.22 square inches. Is everybody okay with that? Again, we have a U-shaped stirrup, so there's 2 bars that are going to cross a given crack. Now, our loads, all right. Okay. We have a self-weight, which we don't know. We have a dead load, which is 1.5. And we have a live load, which is 3 kips per foot. Everybody okay with that? All right. Now help me out. If I'm trying to determine or do a little bit of structural analysis, let's say. Let's do some structural analysis. Okay. If I'm trying to do some structural analysis, you tell me what's my first step? Calculate the beam self-weight. And how do I get the beam self-weight? Unit weight times the area. So gamma times BH. So we'll say so B is 12 inches, 27 inches. Anybody got a problem with that? There we go. And what do we got? 0.3375 or 0.338? Close enough? All right. So what's the next step? There we go. All right, and then plus, what was that, 1.5? Plus 1.6. All right, and what does that give you? $7.006. I have a second on that? Everybody okay with that? Now, help me out. This is a beam with a uniformly distributed load, all right? So help me out. What's the shear diagram look like? It's a line, right? It's a line. All right, what I'm going to do is I want to derive the equation for that line, okay? Now, I want to, let's be clear, I don't need to derive a thing because I've got this. I'm taking this from you. We've got this, so we can look it up. But I have a reason why I'm deriving it. I want to make sure that everybody in here is clear on how to use it. Thank you. Picks up the notebook and everything flies out. Damn it, Dr. Michelson. I had everything organized, man. Messed it up. All right. Does everybody have this? We got this? Okay, I'm going to move on to the next panel. All right. So I'm going to do a little bit of structural analysis, and we're going to bring it back to last semester a little bit, but I really think this is a useful exercise so that you all understand where a lot of this stuff is coming from. So all right. So shear diagram. Okay, so let's see. What do we got? We have a beam that looks something like this, and we have a distributed load. Now, we're going to keep everything symbolic, okay? So I'm going to say this distributed load is W sub U, okay? Now, we've got a support over here. We've got a support over here, and let's see, let's put some dimensions. So, well, first off, would you agree, just based on the loading, that the reactions are going to be the same? Agree with that? And this dimension is going to be L. Everybody okay with that? Okay. Now, help me out. If this was a structural analysis problem, you tell me what to do. Solve for the reactions. And what are one of the things that I do with that distributed load to make my life a little easier? There we go. Convert it into a single point load. So I'm going to say that single point load is probably something about like that. And what is the magnitude of that single point load? W times L. And this distance right here from there to there is, there we go. See, this isn't so bad, is it? Oh, this isn't so bad. Oh, I'll throw some IJK in there if you want. Oh, now everybody's singing a different tune. Huh? What's that? Just JK? Now that was pretty good. That was good. I will give you that one. I was just JK. Pretty good. All right. So help now. Let me ask you this: do I need to? You tell me. Do I need to do the statics to solve for this reaction, or can you all tell me what the reactions are? WL over 2. Do you need me to, or? No. Okay. All right. So I'll say by symmetry. All right. R is WL over 2. Okay. So let's go back to some more basics with structural analysis. So we've got this. Oh, come on, eraser. There we go. All right. So now it's time to draw the shear diagram. And what's that going to look like? It's going to go up. It's going to go down. And it's going to go up, right? Are you with me on that? Okay. So something about like that. About like that. There we go. So this is positive W L over 2 minus W L over 2. All right. Now here's the thing. I don't really care about the moment diagram because we're not doing moment, we're doing shear. Okay? So I really don't care. All I care about is just the shear. Now, you agree that this is a line, right? Based on that graph, does the line have a positive slope or a negative slope? Negative slope. What's the y-intercept? WL over 2. We could take a wild guess as to what the equation is, but let's use a little bit of statics. Let's samurai sword or lightsaber or cake cutter right through this point right here. So when you've got that, what do you have? You've got this, this. You said that was W L over 2. And then you've got that, right? I missed something? Oh, he did miss the cake. Ah. Now, yes, it's Dr. Birthday Boy. Okay, we're cutting a section at some distance x, right? So this is W sub u acting over a distance x, okay? W sub u acting over a distance x. So if I collapse that into a single point load, it's what? WUX. All right, and this distance is x over 2. And we need to determine the unknown shear. Remember, downward shears, right? So I'm going to call this V sub u, but it's V sub u of x. It's a function of x, right? Now there's a moment there too, and I could draw it if you want, but it doesn't really matter. I could put, okay, there's your moment, but it doesn't really matter. All right. Summing forces in the y direction. I have WU L over 2. I've got WU X going down. I've got the shear going down as well. So WU L over 2 equals WUX plus VU of X. So VU of X is WUL over 2 minus WUX. So does everybody see that that is, in fact, the equation of a line? Okay. Now let's also be clear, we can check to see whether or not that works. I mean, oh. Oh. How long's the beam? 288. Let's just do it in feet. So, all right, and what did we say the equation was? We said it's WL over 2 minus WX, right? And so what was W? Well, this is when I'm not being lazy. I'm being exact. So do that. Highlight, insert. You know, so that's easy to verify, okay? So everybody okay with that? Any questions? All right. Okay. If you understand that, then what's coming next hopefully should be pretty straightforward. All right, so, all right, everybody got this? Okay, so everything we've been doing up until now is on the loads, okay? So we know the loads on the beam, the self-weight, the dead load, the live load, all that. Now let's look at the resistance, okay? So, in order to look at the resistance, we need the capacity generated by the concrete and the capacity generated by the shear. Let's start off with the concrete. All right. So let's look at the concrete capacity. So you tell me, how am I going to compute the capacity of the concrete and shear? Let's just start off with the nominal capacity. How about this? VC. Shear capacity provided by the concrete. There we go. All right. Help me out. What's lambda? What's B? Which for a rectangle is just going to be 12, right? So 12, what's D? 24. Okay, so we got 2 times 1 times 12 times 24 times the square root of what? That's right, 4,000. You put in PSI, you get out PSI. So when I do this math, what is V sub C? What are the units going to be? Pounds. Okay. So what does that come out to be? Excuse me.
36,400.
So there we go. Any seconds on that? So maybe 36.43. Is that a fair point? All right. Now, what's phi? What's our phi value? 0.75. So what is phi VC? Well, it's 0.75 times 36.43. And what does that come out to be? $27.32. Do I have a second on that? Okay. Now, help me out with this. Now, this doesn't really have anything to do with our example, but I want to do this off to the side, so note. How did we compute R, the beam reaction? Tell me again how we did that. Okay, so let's do that. So 7.006 kips per foot times 24 feet divided by 2. What is that? 84.07. Do I have a second on that? Okay. What does that tell you, just looking at that? That's the maximum shear. So, but what does that tell you? The concrete can't hold it by itself, right? The capacity, the factored capacity that can be provided by the concrete is only about 27 kips. The beam is seeing 84 kips. So hopefully, just looking at those two numbers tells you that we need stirrups. Okay, is everybody okay with that? All right. Now for the steel, the problem with the stirrup calculation is that there's multiple different regions. How many different regions of stirrup spacings are there for this beam? 4. Okay, so here's what I'm going to do. I'm going to do the capacity calculation for one region, and then you'll see how everything else is just repetitive. So let's look at the steel capacity. And we'll do region 1. Because the only thing that delineates the difference between what's region 1, what's region 2, what's region 3 is the spacing. Okay? So, all right. So for region 1, what is the stirrup spacing? 4 inches. I was getting ready to write it. So V sub S, given a stirrup spacing of 4 inches, how do I compute V sub S? You tell me. You tell me. No. What? Net area. You mean AV, not AN. Thinking steel design.
You have your area of shear reinforcement, right? Then you multiply that by your yield stress of shear reinforcement. Or
D over S. All right. So the area of shear reinforcement is what? Somebody else. No, just getting everybody participate. What's this? There we go. What was the grade of steel for this one? Can't remember. Actually, I can't.
What's the subscript?
Just the tensile reinforcement. To be honest, I don't see why they don't just go with F sub Y, but that's just me. That's just the code for you. And then D over S, D is 24. Okay, so 24 inches over 4 inches. All right, so what is that? 79.2 kips. All right, so that's V sub S. What is phi VS? It's going to be that times what? All right, so that is 79.2 kips. Second on that. And then, now let's look at this. So I've got phi VC and I've got phi VS. So can I compute phi VN? The capacity of the whole beam. And how do I do that? Add them up. There you go. So I'll... All right. That was a thing. All right. So phi VC is, what was that again? Plus 59.4. Now what is that? So what is phi VN? 86.72 kips. Now, help me out. Is that good? Just barely, but it is good, because if I compare this quantity here against this quantity right here, we're good, right? But here's the thing. Let's be clear. As I get farther and farther away from the supports, what happens to the shear in the beam? The forces in the beam? They go down. So this capacity, let's be clear on this. This capacity is based on the shear, or it's based on a spacing of 4 inches, but I'm comparing this against the shear right here at the support. In other words, if all I did was use 4-inch spacing everywhere, okay, here's what it would look like. I would have a, bless you, I would have a shear diagram. Let me use a different color. I would have a shear diagram that looks something like that, right? And I'm just going to, go off to center line. And my capacity would be just a little bit over that, bless you. Would be just a little bit over that. But wouldn't you agree, if I used that same stirrup spacing from end to end, that I would have some massively over-designed sections in the center of the beam? In the center of the beam's hardly seeing any shear at all. Do I really need to use that many stirrups in the center? No, I only need to use that many stirrups right here at the end. You see what I mean? So if you notice, look at the actual layout. As you get farther and farther away from the supports, the spacing gets larger and larger because you don't need that many stirrups. Think about it like this. What if I used 4-inch spacing everywhere? Yeah, the beam would work. Wouldn't it be over-designed? Or wouldn't I be using way more stirrups than needed? Now, let's say you did the math and it was only about 6 or 7 more stirrups on this beam. You're like, who cares? 6 or 7 more stirrups on a single beam is no big deal. Yeah, take that and multiply it by 800, however many different beams you've got in a building, then it starts to matter. All right? See what I mean? So, that is true. So, here's what I'm trying to get at. So this is an actual 2-scale plot of the shear diagram. We're going to look at some of these values here in a little bit. But here is a 2-scale plot of the shear diagram for this beam. And you notice this blue line, those are the loads. That is the forces that we are putting on the beam. And then as we go down the beam, what we find is, okay, right here at the beginning, this was that shear load of what was like 84.07 kips or something like that. And then a factored shear resistance of 86 point something. So yeah, it was pretty economical right here. But if I bump that spacing up a little bit, I can use a more economical selection down the line. Like for instance, if you notice that that first region goes all the way to what, 52 inches? So what's 52 inches in feet? 4 and some change, right? 4.3 something, right? So We go like this, and then once we get here, our capacity drops. Why does our capacity drop? Because right here, our stirrup spacing suddenly increased. See what I mean? Now, there was a very particular reason why we started that 8-inch spacing right here. What if we had started the 8-inch spacing like somewhere over here? Then we wouldn't have enough. We'd have an element that had experienced failure. Exactly. And that is how we're going to design. That very principle. That's how we're going to design. Now, if you're wondering, real quick, if you're wondering where I got the other values on this plot, like this one right here, that's the 4 inches. Well, let's go back to, where am I going? Right here. Let's go back to this right here. Based on a stirrup spacing of 4 inches, I took that stirrup spacing and I computed this. Took that and computed this, took that and computed that. It's pretty direct, right? If you can do one, you can do others, right? So I'm just going to show you a little table of the results. All right, so can I, has everybody got this? All right, so example 12. So I'll say for the remaining ranges, or for the remaining regions, all right, so how many regions were there again? 4. So 1, 2, 3, 4. So let's be clear on the plotting aspects. So when I put a range, let me explain what I'm doing here. So range number 1 goes from x equals 0 inches to x equals what, 52 inches? Right? So help me out, help me fill it in. If this goes from x equals 52 inches, not 55, 52 inches, it goes from x equals 52 to x equals what? 84. Does everybody see that? And this goes from 84 inches to 124. And this goes from 124, 124 to what? 144. And once we get to 144, we're good, because 144 is 12 feet, and that's the middle of the beam. So you can imagine it's like a mirror, you know, just reflects back on the other end. Make sense? So if you've got symmetric loading for like a simply supported beam, you only need to design reinforcement from the support to midspan and then just repeat it. All right. So I'll fill in some remaining values. So S. So we have what, 4-inch spacing? We have what, 8-inch spacing? We have 10-inch spacing, and then what's the spacing out in that center region? There are none. There's nothing there. So we need VS. Okay, now we did this for the 4-inch spacing, and we got what, 79.2? Is everybody okay with that? So if you repeat this calculation for 8 inches, you'll get 39.6. And then for here, you'll get 31.64. But if you have no stirrups in that last region, what is the capacity provided by the steel? 0. Not a thing. So if you calculate phi-VN, so just take that, multiply it by 0.75, and add phi-VC. Over here, we got 86.72. You'll get 57.02. You'll get 51.08. And then you'll get 27.32. So based on these ranges and these phi-VNs, this is how that plot's being generated. It sort of looks like this. What is it? It's going like that, then it drops down, then it goes like that, and it drops down a little more and goes like that, drops down a little more and goes like that, right? That's how that's being done. This is 52 inches. This is 84 inches. This is 124 inches. And then right here, that's the center line, and that's 144. And then it would just repeat from there. Exactly. And then another reason why we derive the equation is because if we just guess, let's say, an S value of 6 inches, what we can do is we can then say, all right, based on an S value of 6 inches, that gives us some capacity, right? We can then determine where can we start using that stirrup spacing. In other words, when does it come in contact with the shear diagram? So we'll need that equation, the equation of that line right there, because knowing that equation of that line, we can figure out, like, where is that point? Where does it start to intersect? And that'll be how we start to space them out. Does that make sense? All right. So hopefully you understand how that plot was generated. I apologize. I held you a little bit longer, but I thought this was pretty relevant. Next time what we're going to do is we're going to start to address the question, how exactly do we take these equations and develop a procedure for spacing out stirrups? So we'll play around a little bit with that next time. That's all I got. Notebooks should be making its way around depending on where it's at. That's all I got. You all have a great day, and I will see you all on Wednesday.